Hello, class. Headed towards our last thing for me to say about integrals, because next week we'll be back to talking about applications of derivatives, so we can review basically taking derivatives before the final. But I wanted to say something more general about what to do if you're faced with finding the area of some shaded region, and that region's not one that involves the x-axis. So if it involves the x-axis, then we've talked about how to express it in terms of integrals and how to handle when it's counted as positive and how to compensate when the definite integral counts it as negative. So we did all of that last week. But here's a more general formula that works sometimes if your area is actually bounded by two graphs, one above and one below. Then if your area is bounded like this, again, by one big function, one small function, x equals a on the left and x equals b on the right, then the area is given exactly by the integral from a to b of the big function minus the little function dx. Okay, or if you prefer, the above function and the below function, whichever way you want to think about it. Now, I should notice this formula is smart. It counts all area as positive. So in particular, if instead of looking like that, your region looked something like this, that's A, and that's B, if you use this formula up here, you will get the exact area of this bizarre wedge shape, and it will not count this area below the axis as negative. Once you use this formula, it throws away all caring about where the area is relative to the axis, which is a huge relief if the thing you want is the area of some shaded region. So please remember, you don't need to compensate for the fact that it's counting area as negative, because it's not counting any area as negative. It's counting all area as positive. Okay. So I wanted to do an example of applying this, and we'll do an example of some of the more intricate things next time. But I'm going to go ahead and pop up a graph for you of a shaded region that's bounded by two curves. And so the two curves that this region is bounded by are f of x equals minus x squared plus 4x, and g of x equals x squared minus 4x plus 10. And so our graph here is this sort of bow tie thing, bounded on the left by x equals 0, and on the right by x equals 4. Okay, so we know by the formula I just gave you that in order to calculate this area, I'm supposed to take the integral from 0 to 4 of whichever of these is the big function, minus whichever of them is the small function, dx. So which of these two functions is the big function? Well, there's a couple ways to do that, to figure that out. Namely, one of them is to see that one of these two bounds is a parabola pointing up, and one of them is a parabola pointing down. But you can tell whether a parabola is pointing up and down by whether the coefficient in front of the x squared is positive or negative. So this one, this is actually the big function, and this is the small function. Alternatively, you could figure out what the y-intercept of these things is and figure out that the y-intercept of f is 0, 0, and the y-intercept of g is 0, 10. So again, g is the one that's bigger. Okay. But anyway, however you decide it, that means that this integral works out to be the integral from 0 to 4 of, and so g is the one on top, so that is x squared minus 4x plus 10 minus, and then minus x squared plus 4x dx. Okay, so I'm going to simplify this thing I'm integrating as much as possible before I integrate it, because it'll make my life easier. So this will be the integral from 0 to 4 of, and so there's a minus x squared, so that's going to give me a 2x squared. I have a minus 4x, so that's minus 8x. And then a plus 10 minus nothing, so plus 10 dx. Okay, so here is our thing we're integrating, again, simplified by pulling together all the terms from over here. Okay. Now, for a bit, we've been doing integrals by u-substitution, but here we conveniently don't even need to do u-substitution. We can just go ahead and integrate this term by term. So this will be 2x cubed over 3 minus 8x squared over 2 plus 10x, evaluated as x goes from 0 to 4, which will be 2 times 4 cubed divided by 3, minus, and then 8 over 2 is 4, so that is 4 times 4 squared, and then plus 40. And we can simplify this number a little bit because this is 128 over 3 minus 64 plus 40. So that is 128 over 3 minus 24. What is 24 in thirds? That would be 72. So this is 128 over 3 minus 72 over 3. And then you can figure out, okay, well, what is 128 minus 72? Well, that will be 56. Okay, and so that will be the area of our region. Okay, so this bow tie region, we found out its area is 56 over 3. Okay, let's do one more example of doing this. So, namely, let's say we're now looking at the function f of x equals x, and g of x equals x squared minus 12. I'll pull up graphs of those two for you, so that will look like this. And let's say I want the area of this region. Okay, sort of like an airplane wing, I guess, roughly. Well, I should figure out which of these is the big function and which of them is the small function. And I can figure out that from the graph, because one of these is a line and one of them isn't, and the line is the one that's the big function. So this is the big function, this is the small function. And I need to figure out exactly what the interval is. And at least from the graph, it kind of looks like the interval goes from 0 to 4, but I can make sure I know exactly where that intersection is. So let's set x equal to x squared minus 12, just to double check that that's at exactly 4, and that it's not at some ugly radical that's really close to 4. So that'll give me x squared minus x minus 12 equals 0. So this is finding the intersection. And so this will be x minus 4 times x plus 3 equals 0. So the graphs intersect at two places, namely x equals plus 4 and x equals minus 3. Okay, but minus 3. So I did that with the whole paper behind the graph, so I'm going to say what I wrote here again. So the intersection, how am I going to find the intersection? I am going to look at where the two functions are equal, x and x squared minus 12. So I'll go ahead and move the x over, so that'll give me x squared minus x minus 12 equals 0. I'll factor it. That'll give me x equals 4 and x equals minus 3. Those are the two places where the graph of x and the graph of x squared minus 12 intersect. But x equals minus 3, that's not in the graph. So that intersection is x equals 4. So when I go to use this formula for the area, the thing I'm going to end up writing down is the integral from 0 to 4, this is the left limit, that's the right limit, of x minus x squared minus 12 dx, which let's work on that. So that's the integral from 0 to 4 of x minus x squared plus 12 dx. And so what is that? That's x squared over 2 minus x cubed over 3 plus 12x, all evaluated as x goes from 0 to 4. Okay, so this is 4 squared over 2, which is 16 over 2, which is 8, minus 4 cubed over 3, that's 64 thirds, plus 12 times 4, which is 48. Okay, and then the last problem I just skipped over is talking about this x equals 0, but I'll say here, I need to subtract off this thing evaluated at 0, but in this specific case, all of these things have an x in them, so when I plug in x equals 0, all of these are 0. So the area just happens to work out to be exactly this, which as it happens is 56 minus 64 thirds. So that's 168 thirds minus 64 thirds. And so this is equal to, at the end of the day, 104 over 3. That is the area of this wedge shape. Okay, in the next video, I'll do a couple examples where we blur the lines and sort of mix this in with some u-substitution integrals and talk about regions that are a little more complicated. But then we'll be done. All right, until next time, be well.